All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandrea, and I'm the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful webinar today on Voyagers 1 and 2, Where Are We Now? And after the presentation, we will have a question and answer session. Before we start, I'd like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Professor Lennard Fisk is the Thomas M. Donahue Distinguished University Professor of Space Science at the University of Michigan. Professor Fisk's list of professional service include many prestigious positions that include the current elected president of the Committee on Space Research, former chair of the National Academy of Sciences Space Studies Board, and the former associate administrator for space science and applications at NASA. Professor Fisk has over 190 publications in solar and heliospheric physics and has numerous awards that include being a member of the National Academy of Sciences, a foreign member of the Academia Europaea, a fellow of the American Geophysical Union, an elected member of the International Academy of Astronautics, an AIAA Space Science Award, the NASA Distinguished Service Medal and the NASA Outstanding Leadership Medal, and the International Academy of Astronautics Basic Science Award. Michael Paul is the program manager at the Johns Hopkins University Applied Physics Laboratory. He has held many prestigious leadership positions in both commercial and UARC institutions within the space industry. Michael is currently the program manager of the Lunar Surface Innovation Initiative at APL and is the program manager of the Interstellar Probe Study at APL. And now for the presentation. Michael, the virtual floor is yours.
Thank you, James, and thank you all for joining us today. The concept of a mission to the nearby interstellar medium is not a new one. In past episodes of this series, you can find detailed descriptions of the history of this idea and why NASA is investing in exploring the idea so earnestly right now. One of the many reasons behind our effort is at the heart of today's discussion. Voyager 1 is approaching 150 AU from the sun, with Voyager 2 not that far behind. Still, and both of these craft are still returning tantalizing data about the edge of the solar system 43 years after launch. And before I forget, happy launch date of Voyager 2. That was in 1977 on August 20th, which is today. And I think it was 15 or 16 days later, Voyager 1 was also launched from Florida. So happy launch date to all the Voyager team. But the instruments on the Voyager craft can't tell us the whole story. They were built for planetary exploration and not for this serendipitous plunge into the space between the stars that it's headed towards. In addition, both the spacecraft will not be able to continue indefinitely. Despite the robust operating success over so many decades, they don't have the power to keep communicating for much longer. The further away they get, the lower the power the radio signal is and the less data we can get off of them. There are other reasons why in the years ahead, not too many years ahead, we won't be able to hear from them again. And so we will lose this ability to continue exploring in situ the boundaries of our solar system. So we're imagining a mission, Interstellar Probe. Next slide, please. Oh, we're already there. Sorry, James. But you can go ahead and next step, please. We're imagining a mission, Interstellar Probe, that can follow these intrepid spacecraft to and through the boundaries of our solar system and out into interstellar space. In this diagram, note the logarithmic scale. You see an artistic representation of the locations of that boundary region. You'll see the termination shock, heliopause, the hydrogen wall. These are based on measurements. The distance that they're at is based on measurements that Voyager has made and other observations. Next step, please. So one of the things that Voyager and the team did that really fascinates me was to turn the spacecraft and look back, taking pictures that together have been called the family portrait, to help all of us see ourselves in context with the planets that make up our family, our solar system. Next step, please. I understand that the family portrait was completed after flying by Neptune, and you can see how much further Voyager has gotten 30 years on from when those final pictures making up the family portrait were taken. Next step, please. And this image here, the pale blue dot, as it's been called, this image has become an iconic picture in space history. Today, we're really pleased to have Professor Len Fisk joining us to talk about the physics of the outer solar system, the boundary between us and what is outside, and what Voyager has told us about this, and share his take on where the craft are with relation to that boundary. But he's not just a physicist. He's not only a physicist. Back in the 90s, he was the head of NASA science, and he issued the approval to Carl Sagan and the Voyager team to take those pictures and make that family portrait. As Professor Fisk told me the story of these images, it reminded me of how deeply personal space exploration is to people who do it like I do and really enjoy their work, but to all of humanity. We all live here, and we all can only live here because of the physics that keep us warm and safe. In Len's case, though, this goes even deeper. He knew the timing of these images, and he told his family, including his teenage sons, to head outside while the pictures were being taken, taking this idea of a family portrait to a cosmic level. And I think that's just fantastic. But we're all in this image, all of us that were born after 1990, before 1990, I should say. Next slide, please. And so as I welcome Professor Fisk today, I also want to thank him and the Voyager team for helping us to see ourselves, to see this pale blue dot of our home. Professor Fisk, the virtual floor is yours.
Thank you very much. My talk today is going to be different, I think, than many of the talks you've heard on the outer heliosphere and its interaction with the local interstellar medium. Not going to show much data, but I'm certainly going to talk about the interpretation of data. Not going to show any pretty pictures resulting from numerical models. And in fact, I'm going to argue that all current numerical models relevant for this problem are wrong. I'm a card-carrying theoretician, but rest assured, I'm not going to overwhelm you with equations. Rather, I'm going to ask you to consider that there's a fundamental property of the region where the heliosphere interacts with the local interstellar medium that has been ignored. And when this property is properly taken into account, the current understanding of the global structure of the outer heliosphere, and in particular where the Voyagers are, has got to change. So let me begin by orienting everyone about the region of space that we're going to talk about. First slide, please. This slide was provided to me by the Interstellar Probe folks, and it seems appropriate for this lecture series. The supersonic expansion of the solar atmosphere, the solar wind blows outward from the sun, creates what we refer to as the heliosphere. There's a termination shock that surrounds the sun, where the solar wind becomes subsonic, and in some sense, and we will talk about that more. And it interacts, merges with the local interstellar medium. The boundary separating the solar wind from the interstellar plasma is known as the Heliopause. The region we're going to talk about today lies between the termination shock and the Heliopause, and it's known as the Heliosheath. We're going to confine ourselves to the nose region of the Heliosheath. That's where Voyagers are. The solar system is moving excuse me, through the local interstellar medium. The nose region of the Heliosheath lies in the direction of motion of the solar system. The tail region, which is in the opposite direction, is less well understood and probably not correctly depicted in this figure. Now, also shown in this figure are the trajectories of Voyager 1 and 2, and this is the subject of today's talk. Where are Voyager 1 and Voyager 2 now? The fact that I even asked this question reveals that I do not agree with the interpretation of the Voyager principal investigators that both Voyagers are now in the interstellar medium, or as they claimed, Voyager 1 crossed the Heliopause in August of 2012, and Voyager 2 crossed the Heliopause in 2018. Voyager 1 was at 121.5 AU when it crossed. Voyager 2 was at 119 AU. Next slide, please. The reason for my skepticism is that, or if in fact you know me well or heard my talks in the past, maybe even outright hostility to the Voyager investigators' claim of the location of the Heliopause, is based on the fact that the Voyager investigators, and for that matter, essentially all numerical models of the Heliosheath, have overlooked and ignored a fundamental property of the Heliosheath. It's well known, we're going to talk about this more, that the dominant pressure in the Heliosheath resides in a particle population known as interstellar pickup ions. Interstellar neutral gas penetrates into the heliosphere, is ionized by photoionization and charge exchange, picked up by the solar wind, and convected into the outer heliosheath. The pickup ions are also accelerated and form a particle population, which I'm going to refer to using the historic term, anomalous cosmic rays, or ACRS, and these also contribute substantially to the particle pressure in the heliosheath. What is not fully appreciated is that in the heliosheath, the pickup ions and the ACRs need to be treated as a separate gas from the thermal solar wind. And if you do not do that, as a starting point for your consideration of the global structure of the heliosheath and its interaction with the local interstellar medium, you will, as we shall discuss, get the wrong answer. Next slide, please. The ACRs, the anomalous cosmic rays, with their unusual composition, this is what makes them anomalous, enhanced in oxygen and not in carbon, were discovered in the inner heliosphere in the early 1970s. The pickup ions, ionized interstellar neutral gas, have the correct composition, and so the theory for the origin of the ACRs was simply the pickup ions are convected outward with the solar wind, they're accelerated to ACRs in the outer heliosphere, and they propagate back into the inner heliosphere. Now, from the beginning of this theory, there was a concern that the pickup ions are, as they are convected into the outer heliosphere, they will be assimilated into the solar wind, creating a single gas of solar wind and pickup ions. This obviously would create a problem for accelerating the ACRs, particularly as was assumed early in the discussion of the origin of ACRs, you wanted to inject them into diffusive shock acceleration at the termination shock. A number of papers were written back then, showing that assimilation into the solar wind was unlikely. The plasma instabilities that equalized the initial distribution of recently ionized pickup ions would result in an isotropic distribution, essentially at the solar wind with thermal speed at the solar wind flow speed, well above the solar wind thermal speed. Next slide, please. And of course, when Voyager 2, with its working plasma detector, crossed the termination shock, it observed that the solar wind was not heated. Rather, it was the pickup ions as a separate gas that are heated. In the solar wind upstream of the termination shock, the pressure of the pickup ions is very much larger than the pressure in the thermal solar wind. It's the pickup ions that are heated at the termination shock, and then again as a separate gas from the thermal solar wind. The pickup ions become the dominant pressure downstream from the termination shock throughout the heliosheath. Now, contrary to expectations, the ACRs were not accelerated to high energies at the termination shock where Voyager 1 and Voyager 2 crossed. Particles were accelerated immediately downstream from the termination shock to a few MeV per nucleon, but not to higher energies. Rather, at both Voyager 1 and Voyager 2 penetrated into the deep heliosheath, the full ACR spectrum to their highest energies were observed. These are the spectra that were determined by George Glecker. Spectra for ACR oxygen at Voyager 1 and Voyager 2, both located at about 118 AU, which is just inside where the Voyager investigators claim the Heliopause is located. George points out that these were early calculations of this spectrum. There are some, they need to be corrected for some systematic errors, which can differ in small ways between the two spacecraft. So although they look exactly the same here, when these corrections are made, there will be differences. But the main point here is that these intensity spectra are well fit by a power law with a spectral index of -1.5 and an exponential cutoff. That's an intensity spectrum, which is what this is, with spectral index of -1.5 corresponds to a distribution function with spectral index of -5, which is logarithmically, there we go, divergent when you calculate the pressure. And in fact, if you consider all the species of ACRs, not just oxygen shown here, all of which have the same spectral shape as Fisk and Gleckler showed some years ago, the total pressure in these high energy ACRs is equal to approximately half the pressure in the pickup ions downstream from the termination shock. Next slide. So the ACRs, of course, are highly mobile. They're completely separate from the thermal solar wind. And so we now have two particle populations, pickup ions and ACRs, which collectively are the dominant pressure in the heliosheath and which collectively are a separate gas from the thermal solar wind. Now, the pickup ions and ACRs are, of course, coupled to the magnetic field. And so the pressure in the pickup ions and ACRs plus the pressure in the magnetic field has to balance the pressure exerted on the heliosheath from the local interstellar medium, which we can take to be approximately constant. The solar wind thermal energy doesn't enter here because it's too small. We are out downstream from the termination shock, and so the ram pressure of the solar wind becomes small and is not important, and it becomes even less so with distance into the heliosheath, since, as we will talk later, the radial flow speed of the solar wind is observed to become quite small. And since the pressure in the pickup ions and ACRs is actually large compared to the magnetic field pressure as well, the pressure exerted by the interstellar medium should be nearly constant. Then throughout the heliosheath, the pressure of the pickup ions and ACRs should also be roughly constant. Now, this requirement of constant pressure in the pickup ions and ACR places constraints on how the ACRs are accelerated in the heliosheath. The pickup ions, with all their pressure, are convected radially outward from the termination shock to the locations of Voyager. The ACRs acquire their large pressure deep in the heliosheath. For the sum of the pressure in the pickup ions and ACRs to be constant in radial distance, you have no choice but to accelerate the ACRs out of the pickup ions as they are convected radially outward. And of course, there's a pump acceleration mechanism that I and George Gleckler introduced a couple of years ago. It performs this required acceleration out of the pickup ions as they are convected outward and yields the correct spectral shape. It is, I think, the most likely acceleration mechanism. So in the heliosheath, we can treat the pickup ions and the ACRs as a single gas, but it's a single gas which is separate from the thermal solar wind. Next slide, please. Now, it's an important thing to know is that the pickup ions and ACRs alter the observed magnetic field. If you have a separate gas of pickup ions and ACRs, they're going to experience gradient and curvature drifts that create currents. And since the pressure is so large in the pickup ions and ACRs, it will create a significant magnetic field. Thus, the magnetic field that's actually observed in the heliosheath consists of two components: the magnetic field that is convected across the termination shock with the solar wind, and the magnetic field that is caused by currents produced by gradient and curvature drifts of a separate gas of pickup ions and ACRs. This very same effect happens in the Earth's magnetosphere. The ring current is a separate gas which creates a magnetic field that offsets the Earth's magnetic field, resulting in an observed magnetic field that is less than the Earth's intrinsic magnetic field. Now, in a paper in 2016, Fisk and Glechter, we provided a method for unraveling the observed magnetic field to find the magnetic field that is embedded in and convected outward with the solar wind through this simple formula shown. Here, B is the observed magnetic field, B sub SW is the magnetic field embedded in the solar wind. Next slide, please. The pressure in the magnetic field embedded in the solar wind is the principal force controlling the flow of the density of the solar wind in the heliosheath. Thus, if you want to build a self-consistent model for the heliosheath, the pressure in the pickup ions and the ACRS is in equilibrium with the observed magnetic field and satisfies this first equation. The observed magnetic field and the embedded magnetic field in the solar wind satisfy the second equation. The embedded magnetic field in the solar wind and the flow velocity and density of the solar wind satisfy the standard MHD mass and energy equation shown at the bottom. Rho is the density here, U is the solar wind flow velocity, P sub SW is the solar wind thermal pressure. And I emphasize again, it is the magnetic field embedded in the solar wind, not the observed magnetic field, that controls the flow of the solar wind. Next slide, please. Now, there's really some first thing to note here, which makes life remarkably simple doing this problem. When you start from approximately constant pressure in the pickup ions and ACRs, the flow of the solar wind must be in a plane that contains the magnetic field. You've got gradient, and if there are gradients in the pressure of the pickup ions and ACRs, which is the dominant pressure force in the solar wind, they can only be relieved along the magnetic field. Thus, the solar wind cannot diverge in a direction perpendicular to the plane containing the magnetic field, since this would introduce unacceptable gradients in the pickup ion and ACR pressure. The magnetic field in the heliosheath lies primarily in the azimuthal or T direction of the RT and coordinate system of Voyager. Thus, significant flows of the solar wind in the polar direction or N direction are not permitted. It's possible that immediately downstream from the termination shock, there can be some polar flows introduced by the shape of the termination shock. But as the solar wind flows outward through the heliosheath, it must be primarily in the RT plane. And indeed, this is what Voyager 1 observes. Voyager 1 does not have a working plasma detector, but Courageous and Decker with their LEP detector have used the convective anisotropies of low energy energetic particles to infer the solar wind velocity, particularly in a direction perpendicular to the magnetic field. Courageous and Decker's instruments measurements are generally in the RT plane, but the Voyager 1 spacecraft was rolled a number of times, and indeed there were no polar flows, particularly in the heliosheath, ahead of the location of the Heliopause claimed by the Voyager investigators. Voyager 2 does have a working plasma detector. It sees some but not large polar flows. However, these measurements are very suspect. With the orientation and sensitivity of the sensors on Voyager 2, only a small fraction of the solar wind distribution function is observed, and it's impossible to determine a gyrotropic distribution function, which the solar wind undoubtedly has. And so in all likelihood, the polar flows measured by Voyager 2 are overstated. And so both Voyager 1 and Voyager 2 show no evidence of strong polar flows. Now, this requirement that strong polar flows are neither allowed in the heliosheath with the dominant pressure in a separate gas of pickup ions and ACRs, nor are they observed, basically eliminates every model of the heliosheath with the heliopause that is a hard barrier with the interstellar medium. In other words, a heliopause, which is a tangential discontinuity. The magnetic field is convected outward to the heliopause. Where does it go when it encounters the heliopause that is a hard boundary? No solar wind across the heliopause, no component of the magnetic field normal to the heliopause. The only possibility is the solar wind with its embedded magnetic field flows in the polar direction, which is neither allowed nor observed. Now, we should also note that the requirement that the pickup ions and ACRS must be treated as a separate gas invalidates essentially all numerical models of the heliosheath, since most current models are single fluid models. The solar wind, the pickup ions, and I suppose to the extent that the models considered the pressure in the ACRS at all, they are treated as a single gas with a single equation of state. There have been some recent models by Merav Ofer, who made the first serious attempt to treat the pickup ions separately, but the model does not go far enough to recognize the dominant pressure in the pickup ions and ACR and its control of the solar wind. Next slide, please. Fisk and Glecker, 2014. This was a seminal paper of this model. We developed an analytic model for the flow of the solar wind that satisfies all the constraints that we have discussed. The dominant pressure in the pickup ions and ACRs controls the heliosheath. The flow properties of the solar wind are determined by the embedded, not the observed magnetic field. And the flow is in the RT plane of the Voyager RTN coordinate system, the plane containing the magnetic field. The model was developed to explain the observations of Voyager 1, which has a directory into the nose region and the general direction of motion of the heliosphere through the local interstellar medium. The figure on the left is figure 1 from the original Fisk and Glecker paper. The smaller figure on the right is from Fisk and Glecker 2016 and is a better description of the magnetic field in this region. In the left figure, the analytic solutions for the streamlines of the solar wind are shown in red. The figure is a projection of the RT plane onto a rectangular plane. And since the solar wind flows only in the RT plane, it can escape the nose region of the heliosheath only by turning in the azimuthal direction and flowing backwards back into the tail, or by flowing out across the heliopause, which is way out here in this model, much further than when Voyager 1 and 2 thought it to be. It's, and of course, when it reaches the heliopause in this model, it flows into the interstellar medium, and that requires that the heliopause is a rotational discontinuity across which there is a normal component of the magnetic field and flow of the solar wind. There are certain properties of rotational discontinuities. In particular, the plasma density must be continuous across the discontinuity, which requires for the heliopause that the density of the solar wind immediately upstream of the heliopause equals the density of interstellar gas downstream. Thus, along any magnetic field line that intersects the heliopause, which is shown more clearly in the figure on the right, we should expect that the density will be the density of the local interstellar medium. The flow of the solar wind in the heliosheath must decelerate in order that the low density immediately downstream from the termination shock increases to become equal to the interstellar density. Remember the hierarchy here. And the ACRs and the pickup ions determine the observed magnetic field. The observed magnetic field determines the embedded magnetic field, which in turn determines the radial flow of the solar wind. If you calculate the sound speed using the pressure in the pickup ions and ACRs and the density in the solar wind, it exceeds the solar wind, the flow speed of the solar wind. Thus, immediately downstream From the termination shock, the solar wind begins to adjust to its flow speed so that in a steady state, it can flow with the correct density and speed across the heliopause, exactly as Cremides and Decker observe that it decreases. When the radial flow speed decreases, the streamlines diverge, creating a region referred to as the centerline region. The solar wind should flow freely along the magnetic field, filling the centerline range and maintaining uniform density along the magnetic field lines. Further into the heliosheath, the azimuthal speed goes to 0 before the radial speed, and the streamlines turn radial and flow outward across the boundary, beyond which the spiral magnetic field shown in the figure on the right is no longer confined to the heliosheath, but rather intersects the heliopause, which is a rotational discontinuity. In this figure, we labeled the boundary between where the field lines in the heliosheath remain in the heliosheath and where the field lines connect to the interstellar medium, the helioclip. Because when a field line connects to the heliopause, the ACRS can escape, resulting in a precipitous decrease in the ACR intensity and for the galactic cosmic rays to enter. Now, the boundary where the precipitous decrease of the boundary where the precipitous decrease in the ACR intensity has been labeled the heliopause by the Voyager investigation is not the heliopause. Rather, it is simply the location that separates the magnetic field lines that remain in the heliosheath from those that intersect the heliopause. Now, in this 2014 figure, we expected that Voyager 1 would encounter a sector boundary, which separates regions of opposite magnetic polarity beyond the helioclip. The radial speed of the solar wind is very small in this region. It's slowed down in order to get the density right. We estimated that it was only in this figure, only about 5 kilometers per second, in which case the sector boundary should have been observed. None has. And so the outward flow speed of the solar wind must be at least 7.5 kilometers per second, a small difference, but significant for observing sector crossings. Next slide, please. So, what were the observations of Voyager 1 when it crossed the heliopause that caused the Voyager investigators to declare that with such certainty that the boundary was the actual heliopause? The first thing that was observed was the precipitous decrease in the ACRS, which was accompanied by an abrupt increase in the galactic cosmic rays, or GCRs. Prof and Enas observed that there was no change in the direction of the magnetic field across the boundary, which initially led them to conclude that the boundary was not the heliopause, since surely if the magnetic field beyond the boundary is the interstellar medium, it should have a different direction. The magnetic field in the interstellar medium should have a different direction from the Heliosheath magnetic field. Prof and Enas did note that the magnitude and turbulence level of the magnetic field changed significantly across the boundary. But then Don Gurnett observed plasma waves, from which it was possible to determine the plasma density. Remember, Voyager 1 does not have a working plasma detector, and these were the first real plasma density measurements. And Don observed a density comparable to what he expected the interstellar density to be, and he declared that Voyager 1 is in the interstellar medium, and he convinced the other Voyager investigators that Voyager 1 is the first spacecraft, the first human-made object to penetrate into interstellar space, and the announcement was made to the whole world. Next slide, please. Next slide. So, why were these observations not conclusive evidence that Voyager 1 crossed the heliopause? And in fact, they were not in fact the correct interpretation. On the right of this, on the right side of this figure is the explanation in the Fisk and Gleckler model. A precipitous decrease in ACRs and an increase in GCRs resulted simply because Voyager 1 crossed onto field lines connecting the actual heliopause, permitting the escape of ACRs and the entry of GCRs. The no change in direction of the magnetic field was what should be expected, since the solar wind is simply being convected across the boundary they called the heliopause. As for the change in magnetic field direction and magnitude, and decrease in change in magnetic field magnitude and decrease in turbulence, the presence or absence of the ACRs, as we talked about, dramatically changes and can explain the observed changes in the magnetic field. The density that Garnett et al. Observed was simply due to compressed solar wind. There was, in fact, a later analysis by Berlage and Enas in which they looked at a sector boundary just inside the precipitous decrease in the ACRs, where the precipitous decrease in the ACRs occurred. They found it was oriented perpendicular to the equatorial plane of the sun, which is the expected orientation of the heliopause. And they declared this sector boundary to be the heliopause. Their analysis, however, did not correctly determine the transit time of the sectors through the heliosheath, and so their so-called heliopause is simply the large-scale heliospheric current sheet, which at solar maximum conditions can have an orientation perpendicular to the solar equatorial plane. And so there never was any conclusive evidence that Voyager 1 passed into the interstellar medium in 2012. Certainly no evidence sufficient on which to make a pronouncement as profound as the humankind has left the solar system. Next slide, please. So, what about Voyager 2? We don't have a model like we have for Voyager 1. For Voyager 2, it's located on the flanks of the heliosheath in the southern heliospheric hemisphere. We can guess that there will be differences from the model that was used to explain Voyager 1, but not really major ones. What then did the Voyager investigators observe? Well, the ACRs ran away and the GCRs increased. The only difference was the decrease in the ACR intensity was not as precipitous as might have been expected with Voyager 2 on the flanks. The magnetic field strength increased, but there again, there was no change in the field direction across the boundary. And although Garnett did not have any density measurements immediately at the boundary, he observed a density comparable to the expected interstellar density just beyond. There were, of course, plasma density measurements on Voyager 2. It has a working plasma detector. But as we talked about, because the plasma detector on Voyager 2 can see so little of the distribution function, the true accuracy of the density measurements is highly suspect. As nearly as I can tell, the Voyager investigators looked at the observations of the Voyager 2 crossing at the boundary, decided it looked very similar to the Voyager 1 crossing, which they had already decided was the heliopause. And so the Voyager 2 boundary must also be the heliopause. There is thus no conclusive evidence that Voyager 1 crossed into the interstellar medium in 2012, nor did Voyager 2 cross into the interstellar medium in late 2018. Next slide, please. So let's return to the theme of the talk. Where is Voyager 1 and Voyager 2 now? Well, Voyager 1 has been cruising through the heliosheath beyond the helioclif, heading for the actual heliopause. Question, of course, is why haven't we come to it? It's been 8 years now. Well, first comment, it's not clear to me that anyone's really watching to know whether or not we've encountered the heliopause at all. There doesn't seem to be a lot of active analysis of the Voyager 1 magnetic field data, which if the heliopause is a rotational discontinuity, it should be the critical data. And of course, the model with a very simple rotational discontinuity, a sharp, simple rotational discontinuity, that may be an oversimplification, so we're not sure exactly what we're looking for. There is a simple argument you can make using Faraday's law and the likely shape of the heliopause to determine the distance of the heliopause along the center line, which is essentially the Voyager 1 trajectory. And you find some remarkable result that the distance from the center line to along the center line, from the termination shock to the heliocliff, where the boundary where the ACRS escape, is equal to the distance from the heliocliff to the heliopause. Well, Voyager 1 crossed the termination shock at 94 AU and the heliocliff at 122, or a distance of 28 AU, and 28 AU beyond the heliocliff is 150 AU for the location of the heliopause. Voyager 1 will get there in September. Now, it's a simple calculation, lots of simplifying assumptions, but perhaps it's not unexpected that Voyager 1 has not yet reached the heliopause. Well, how about Voyager 2? No simple model here. However, in Gleckler and Fisk 2015 paper, we used IBEX ENA observations to estimate that the width of the region between the heliocliff and the heliopause along the trajectory of Voyager 1 is 4.2 times longer than it is along the width, longer than the width of Voyager 2. If the distance from the heliocliff to the heliopause at Voyager 1 is 28 AU, at Voyager 2, the distance is 6.67, 6 2/3 AU. Voyager 2 crossed the heliocliff at 119 AU, and thus by this simple calculation, Voyager 2 should encounter the heliopause at 125.67 AU, or at the end of this year. Again, we will know only if somebody is watching. All this says to me is that if we're ever going to agree on the global structure of the heliosheath and how it interacts with the local interstellar medium, we need better data with modern instrumentation to fully observe the plasma, the pickup ions, the ACRS, the magnetic field, etc. Over to you, Interstellar Probe. Thank you very much.
Thank you very much, Professor Fisk and Michael, for those wonderful presentations. We're now going to have our question and answer session. So the first question from Abigail Reimer is, what direction out of the solar system would Dr. Fisk like an interstellar probe to go?
In the same direction as Voyager 1. I mean, like, listen, if you go in the tail region, I think in many models, you know, you're gonna be going for a while. It's maybe in a wake. I mean, who knows? It's going to be a complicated story. The nose region is in some ways, in fact, determines everything that happens in the tail. So head in the nose, just like Voyager 1. We only have one probe. I suppose I'd do it Voyager 1. It'd be nice to have multiple data, but I would and get there with, you know, one of the things about Voyager, the whole pickup ion population is not observable directly. You know, you have a plasma detector, and sometimes, and 40 kilovolts or so, you start your energetic particle measurement. You know, that's the dominant pressure force is not observed directly. So take some instruments out there that do that and get in this region where which is really the determining region of the whole shape of the Heliosheath, and its interaction you're doing your interactions on the nose. Go to the nose.
Thank you very much, Professor Fisk. And our next question is also for you, Professor Fisk, and it's from Michael Zemkov, and it's, what would be the observational smoking guns of Voyager 2 having crossed into the interstellar medium?
Well, this, of course, was the, you know, if you say when the Voyager investigators, you know, crossed and they saw a density, Garnett saw a density that looked like interstellar density, there was no sign that said, welcome to the interstellar medium, right? I mean, it's a density, plasma density. And as we said, it comes from compressed solar wind. So if you say, now, if you go to the model that I'm proposing and say, you know, the real heliopause, well, it isn't going to look like what you're seeing at the moment. I suspect that it'll be a turbulent region. You're going to be in the front end of the you know, the heliosphere sheath, you know, pressing into the interstellar medium. I expect it to be turbulent. I expect it to be, there'll be changes, serious changes in field direction. I mean, you're going to know when you get there, because it is going to be obviously different from where you were. And so that would be the signs that I think you'd look for. You'd look for real changes. Now, you know, we're so limited on Voyager because you have, you know, you don't have working plasma detector on Voyager 1 at all. You know, you don't have lots of things you don't have. But if you were flying with Interstellar Probe, for example, you had all these instruments, you know, this is a very unusual region between our helioclif and the heliopause. It's kind of quiet, it's benign, it's kind of dull, frankly. But you hit that real boundary, and it's going to be a whole lot more interesting, and you're going to know it.
Thank you very much, Professor Fisk. And our next question from Verley Sturkin is, what could the role of dust be, especially the small interstellar dust that cannot enter deeply into the heliosphere and might be in larger concentrations near the heliopause, beyond the physics in your model and on the conclusions? This is for you, Professor Fisk.
I don't know the answer to that. I'm sorry. You know, one of the, you know, throughout my career, I've sort of left certain things out. Dust was one of them. Sort of bothered me. You know, I like to think about dust. It's important. I don't know, but I can't tell you. I'd have, you know, if it's going to change, I mean, it would have to change the plasma physics, right? And so you say to yourself, you know, what is the plasma physics that is, you know, which would be affected by the dust? And that, of course, I suppose depends on the charge of the dust and a variety of other things. So you need more numbers to say, would it affect my model or not? And if somebody has them, that'd be interesting to put in, but I don't have them.
Thank you very much, Professor Fisk. And the next question is from Elizabeth Gavilan. And question one is, do light and heavy ions detected by the CRS behave differently across the Voyager 1 and Voyager 2 trajectories? And can they be evidence of an interaction with the interstellar medium? And as a follow-on, in September, will Voyager 1 and Voyager 2 instruments show very different signals than in 2012 and 2018?
I'm a little lost here. What part of the CRS instrument was the question addressed to? It said something about light elements or something. What am I?
Sorry, do the light and heavy ions detected by the CRS behave differently across the Voyager 1 and Voyager 2 trajectories? And can they be evidence of an interaction with the interstellar medium?
Well, in the current, I mean, you know, I showed two spectra there for Voyager 1 and Voyager 2, you know, which were inside the you know, inside the helioclif, you know, I pointed out that there's a similarity to the things, so that's not a big difference. Now, I mean, when you start talking, when you see galactic cosmic rays, for example, CRS sees a lot of those things. You know, part of it is the entry of those galactic cosmic rays. So if you take the model we just had, the heliopause is out there someplace. You know, both Voyager 1 and Voyager 2 are still in the still in the heliosphere. You know, in the heliosheath, you know, obviously the cosmic rays get in because they penetrate, you know, across the heliopause in this model, but since Voyager 1 and Voyager 2 are located sort of different distances from the heliopause. I mean, you know, I pointed out Voyager 2 is close now. Voyager, but it's on the flanks. That's a different place. Voyager 1 is going down the center line, a different place. And so there's a sort of a cosmic ray, it's called cosmic ray modulation. You know, obviously the cosmic rays get in quite freely, but you could have a situation where there is some change in the density, a change in the intensity, because of if you have to propagate from the heliopause to the center line, or do you have to hop to the heliopause to a spacecraft more on the flanks? I mean, those are interesting studies to do. If you compare the difference, it's one of the things we do with cosmic rays. You use it as a sort of the ability to probe places far away. I mean, you know, that's what modulation theory in the inner heliosphere has always done. It sort of tells you about conditions in the polar region, the outer heliosphere, because cosmic rays are affected by that as they come to your spacecraft. Such effects could occur. They might be small because the cosmic rays can propagate freely, but nonetheless, it might make an interesting study.
And as the follow-up for the second question, in September, will the Voyager 1 and Voyager 2 instruments show very different signals than in 2012 and 2018?
Well, if you really do run into the real live heliopause, you know, and again, take that calculation with a grain of salt. It was a simple. But it's supposed to, in the case of Voyager 1, it's not to alarm you that you should have seen the heliopause. But when you see it, you're sure it's going to see something different than you saw in 2012. And then Voyager 2 sees something at the, you know, towards the end of the year. If that's true, it's certainly going to be different than they saw in 2018. I mean, because as the first question, or one of the earlier questions said, what is it going to be like? It's going to be, it isn't going to be, you know, just this nice, calm, benign heliosphere, the outer heliosphere that we're looking at the moment. It's going to be a lot more exciting because, you know, it's like, you know, when you look at the wake off the front of a boat, I mean, you know, right there at the bow of the boat, you know, there's flows and turbulence and, you know, waves and all those sorts of good stuff. So I can't imagine that if it's, I mean, this is the beauty, by the way, of this theory is, you know, if you're a fan of Interstellar Probe, and you're worried about the fact that you know, the interstellar medium looks like what the Voyager 1 people think it looks like. It's dull as hell, frankly, at the moment. But if this is just this sort of benign region between the helioclif and the heliopause, when you get beyond the heliopause, the real one, you know, life gets more exciting. I hope Voyager gets to see it, and I hope you guys get to measure it correctly.
All right, one final question, and that's from Ralph McNutt. Some have suggested that a trajectory offset from the nose direction would allow an ENA imager to assess the length of or absence of a heliotail. Such an imager was not on either Voyager. How might this affect the desired trajectory?
I'm sorry, tell me that one again. I mean, is the question, I mean, ENA, I mean, we observe the ENAs at Earth, right? But you want to have an ENA detector on an interstellar probe? I mean, was that the question? Can you help me?
Yeah, actually, Len, I could perhaps
asking this.
Sure. Oh, well, I'll let Michael go.
Yeah. So so Ralph is basically asking if we had an ENA imager on the Interstellar Probe spacecraft and went out offset from the nose enough that we could see ENAs being emitted from the tail region, then could we see whether or not the tail exists with great certainty? And how might that affect the desired trajectory direction? Because if we went out straight through the nose, ENA emissions through the entire breadth of the solar system coming to the spacecraft would be hard to distinguish from ones that are originating on the far side of the solar system. So basically get offset and be able to look at it from the side a little bit.
You could do that. I mean, first of all, I wouldn't imagine I'd be willing to spare the mass. on Interstellar Probe for an instrument that is in some ways kind of limited in this regard. The subject of ENAs is an interesting one because particularly there have been measurements, for example, of Inca on Cassini and of course the IBEX measurements, and which for the energetic ENAs, relatively energetic ENAs, which really imply that there's a sort of spherical heliosphere. It doesn't have a tail. The difficulty with those measurements is all you're really measuring is that the ACRS, the accelerated particles, are in fact in a symmetric environment. You don't know, what, and you can construct models like that, but it doesn't tell you about, the tail and the plasma physics and things and others, going down the tail. That's an interesting discussion, I think. I think it's, I would be more concerned, I think, with, maybe if you put it, just don't send it too far to the side. Don't get out of the direct nose here someplace. But, and then there may be some things you can do because it, it would allow you to, sort of really make a measurement of the, what you really want to know is the lowest energy ENAs, because those are the ones that are going to come from the plasma. And of course, the difficulty is, when things are flowing down the tail, of course, the Doppler shift of the ENAs, doesn't actually help you. It's hard to see those particles. So a lot of things to think about there. I guess if I were, this is one of those cost-benefit trades. Is this thing, sufficiently important, to get what you want, that it's worth, putting on your probe?
Thank you very much, Professor Fisk. And that's all the time we have for today. Thank you very much to our panelists, Professor Fisk and Michael Paul, and thank you for attending today's webinar. The next webinar will be on Thursday, September 3rd at noon Eastern Time, where we will have a presentation by several members of the Interstellar Probe Study engineering team on the current status of the mission trade space. Please visit the Interstellar Probe Study website for more information about the study and to view information on future webinars and events. Also, please consider signing up on our listserv under the community involvement section of the website to make sure that you are getting the latest information on the upcoming webinars and events. Thanks for joining us and have a wonderful day.